Resonance. Okay. Why did we make that bond? Well, resonance did it. Okay. Why did we break that bond? Resonance did it. Okay. In theory, your instructors in the future will be aware that you are immediately just gut impulsing writing resonance and ask for something a little bit more than that explanation, like maybe to draw some structures on top of it, but maybe not. Maybe you'll get lucky and they will just accept resonance. Go, oh my gosh, how did you know that? Didn't know it, I just knew that that was the most likely answer. Okay? The next most likely answer after resonance, just out of curiosity for organic chemistry, size. You can go into organic chemistry with those two answers. Anybody asks you why, you say resonance. They say, no, that's not right, you say size. Oh, now I'm right. Okay. Hugely important concepts. The reason I organize my rules in this fashion is that allows for you to see resonance or the opportunity for resonance to occur much, much earlier and easier than what the textbook suggests and what other methods have suggested. Okay? So the idea behind this is just an organization, a thought process. You do not have to follow these steps unless you're being asked by me. If I ask you, then you get to follow the steps exactly as I tell you to do them. Okay? So to start off, rule number 1, total all the electrons that need to go into the structure. What electrons are going to go in to explain Lewis structures? Why the valence electrons? Lewis structures are all about bonds. What electrons make bonds? Valence electrons. Okay? So the material that we learned about electron configurations and what makes the valence shell, you need to know that to be able to start Lewis structures. If you don't know that, you can't apply your Lewis structures appropriately. The next big piece of it is you're going to have to watch out for counting charges. Okay? This one's been floating around for a while. If you see a positive charge, what happened? You have to lose electrons, which seems very counterintuitive. Why? If we got a positive value, why would we lose something? Does that make sense? If we lose something, we get smaller. You're right. You are getting smaller. You're getting smaller negative charge. A smaller negative charge is more positive. Okay? So you get that double negative getting in the way. So be aware of that. We'll go through a couple examples translating that English into math and math into English in a little bit. The next part is choosing a central atom. That central atom will act as a connector or bridge, which means there are some atoms that just don't do a good job of doing that. Hydrogen is a very characteristic one. Hydrogen will never be a central atom because it cannot bridge two other atoms. Okay? It can only form one bond. Typically, your halogens will only form one bond. Typically. They can be forced to make other bonds. Okay? But our rule still holds. Our central atom will usually be the least electronegative. Okay? Again, usually. We'll then add electrons in pairs into the structure. Where do we start putting our electrons? What's that? I didn't hear what you said. So we could start putting them in the lowest energy level if we were putting them into an atom. We're not putting them into an atom, though. We're putting them into a Lewis structure. We're going to put our electrons around the most electronegative element first. Why that element first? What is electronegativity? Define it. The ability to attract, that's half of it. Anyone going to give me another half? Ability to attract electrons. Very, very close, but actually still wrong. What is the definition of electrochemistry or electronegativity? The ability to attract, you got it? Bonding electrons. So why do we want to put our electrons around the most electronegative first? Well, these electrons are being put in to act as bonds. Which atom would take the electrons? The one that's most electronegative, by definition. Okay? Which atom is the most electronegative on the periodic table? Fluorine. The least? Cesium. Okay? Having that general trend will help you assign where you put the electrons into your structure. That could be the central atom. That could be the exterior atoms. It all depends on what the actual atom is, or the molecule is. We'll go through and add these electrons until we've achieved an octet, okay, around the atom. There is a slight caveat to that. It's not always 8 electrons. Why is it not always 8 electrons? What's our exception? Which atom won't have 8 electrons? Hydrogen. Why will hydrogen not have 8 electrons around it? What's its electron configuration? 1s1. How many electrons can we fit into just the s orbital? Only 2. Okay? Our hydrogen will cap out at 2 electrons. Pretty much every other element that we'll work with can cap out at 8 electrons. Why? What happens when we move to the second row? Not only do we have s orbitals, we have p orbitals. What's the total amount of electrons we can put in the second energy level? 8 electrons into our second energy level. There's our octet rule. Okay? What happens if we go down into our third or fourth energy levels? We start getting d orbitals showing up with us. Okay? For your sake, don't worry about them. Okay? You don't need to stress about the d orbitals or their contributions. We are only concerned about the s and p orbitals, so we're looking at our octet rule. If we do push into the lower energy or higher energy levels, our lower rows, say sulfur, arsenic, okay, anything below 3 or 4 in the row, we can exceed the octet, okay, but we'll never go less than 8 electrons-ish. Okay? So we'll continue to add the electrons, jumping from most electronegative to the next most to the next most until we've put in the total electrons that we counted up in step 1. Okay? Once you've got all of your electrons accounted for, you can then decide to convert pairs of electrons between the atoms into a line to connect those atoms. This is a really common question that's been popping up. Let's see if I can do this right. Bethany, can I get you to raise your hand? Okay, everybody see Bethany? Okay. What do we mean about electrons between atoms? Okay. What is between Bethany and myself? Those tables? Just these tables. How about those people? Those people between Bethany and me? No. Sean, can I get you to raise your hand? Good. I knew your name. Is Sean between me and Bethany? Yes. Bethany's right there. Bethany, can I get you to raise your hand again? Where's Sean? Is Sean between me and Bethany? No. Okay. We're looking at what's directly between us. So when we're looking at trying to convert our electrons into these lines, we have to evaluate the electrons between those atoms. Okay? Once we've done that, we can now move on to Rule 6. We will start moving non-bonding pairs of electrons towards atoms that have not satisfied their octet. Okay, what do I mean by that? What atom would not satisfy its octet? No. What is the octet? Has to have 8 electrons. What if we draw out our structure and we have an atom that doesn't have 8 electrons around it? Has 6. It hasn't satisfied its octet. We haven't finished. Look at Rule 6. What do we need to do? Find a non-bonding pair of electrons nearby and move it towards that atom so that it can then share and get its octet. Okay? What happens if there's more than one pair of electrons that you could move? Well, technically, if there are more, or there's more than one pair, and they're all from the same type of atom, say 3 different oxygens, you have to show that all of those oxygens are just as likely to share the electron as any one of them. What does that mean? Your answer is going to have multiple structures. You have to account for all of those structures because only one of them shows one atom sharing, not the others. Okay? That is resonance. Okay? The last rule, we're going to tweak that a little bit because apparently we aren't going to do per atom. We're going to do per molecule. How do we specify the charge on our molecule? What was that?
No, that's stupid.
Let's see, which way were you pointing? I was trying to pull another way out of it. How do you specify the charge on, let's say, ammonium? What's ammonium's formula? Ammonium is NH4. Is ammonium charged? How do you know it's charged? Positive. Okay, good. It's +1. How do we know ammonium is charged +1? How would we write that information down? Upper right-hand corner, we write a plus charge. How do we specify our Lewis structure is charged? Upper right-hand corner, we write the charge. Okay, the exact same thing. Okay, so let's take a look at some examples. Which one do I want to do? Let's do, I guess we'll go ahead and do ammonium, and we'll do the SO3. Okay, so these will be our problems. So to start out with ammonium, how do we start? Total valence electrons. How many electrons does nitrogen bring in? Okay, we heard some questions on that. It should be 5 electrons. How do you know it's 5? Anybody tell me why? What's that? If we take a look at the Roman numeral above nitrogen, what's the Roman numeral? 5. The Roman numeral is 5. Okay, so how many valence electrons does it have? 5. What's the non-Roman numeral above it? 15. What's that ones digit number? 5. How many valence electrons does nitrogen have? 5. How else can we figure it out? We count from left to right.
Right to left.
Oh, you could do it that way. It's not going to matter. To get to nitrogen, we start here. We need 1 electron, 2 electrons, 3.
Watch your feet.
That could have been really bad. I know. 5 electrons. I want to avoid this side of the room now. Okay. So we've got 5, or a couple different ways to determine those valence electrons. Okay. How about nitrogen? How many valence electrons does nitrogen have? Nitrogen has 1 valence electron. How many hydrogens? Let's try that again. Let's just start all the way over. How many valence electrons does nitrogen have?
5.
We've now accounted for nitrogen, so let's move to the next atom, which is hydrogen. How many valence electrons does hydrogen have? 1. We have to count the valence electrons for every atom. So we could go plus the next one, plus the next one, plus the next one. Seems a bit redundant, so what do we do instead? We can then just multiply it by 4. Multiplying the right one. Yeah. Okay, so we've accounted for our nitrogen and our hydrogen. What's the last thing we need to account for? The charge. Whoops, let's not do that. How do we get a positive charge? We have to lose an electron. What is the mathematical symbol for losing? A minus. 1 electron. What is our total now? 8 electrons. So our -1 was our charge, or accounting for our charge. Why is that tricky? Our charge was what? +1. And what did we do? We subtracted 1. Why do we do that? What's the charge on our electron? Our electron is negatively charged. Okay, so what are we trying to evaluate in this case? If we start neutral and I lose something, actually we can even do this. Our electron is always going to be -1. To get a positive, what do I have to do? What's the operation that has to happen? Must subtract. What if I want a negative charge? The only thing we can move is our electrons. What's the mathematical operation? I must plus. Okay. What does plus mean in English? We added an electron to our structure. Okay? Questions about that? I'm going to erase it. Okay. So what's our next rule? Next step. Pick our least electronegative atom as our central atom. What's our central atom going to be? What's our least electronegative element?
How do you determine that again?
Which is our most electronegative element on the periodic table?
Fluorine.
Fluorine is our most electronegative, our least electronegative. Cesium. Which is closer to fluorine, hydrogen or nitrogen?
Nitrogen.
Nitrogen. Which was most electronegative, fluorine? Fluorine. Which is closer to fluorine?
Nitrogen.
What's the electronegativity of nitrogen? Higher or lower than hydrogen? It's higher. So which element would we predict, based on our little rule, to be our central atom?
Hydrogen.
Which atom is supposed to be our least electronegative? Hydrogen. What's the issue with hydrogen being a central atom? It cannot bridge. Okay? So you are saying the correct answer in jumping to nitrogen as the central atom, but you need to make sure you understand the rules behind why nitrogen is the central atom. It has nothing to do with the electronegativity. In this case, it has to be able to bridge. Okay? We can then scatter our hydrogens around it. Why do I scatter them in this set? We want to get them as far away from each other as possible. So this happens to span that out a little bit. There's another thing that we could look at. Why did I not draw them, say, on the diagonal, out this way, here, and here? Lewis's theory assumed what? Cubes was Lewis's theory, right? We condensed Lewis's theory into a square. Why did I pick it like that? Because each of the hydrogens is on one side of the square. Okay? So we are still holding true to some of Lewis's assumptions. What's our next step? I believe the steps are up there. Add electrons to the most electronegative. Which element is the most electronegative? Nitrogen. So we'll start putting our electrons in. We'll put them in pairs, and I will preferentially put them between atoms if I have the option. Why should I do that? What was Lewis's? What was that?
Because they're bridging.
Kind of. We're trying to make a bond. Okay? Bonds require electrons between the atoms. So if I'm given the option, I'll go ahead and put the electrons between the atoms first, and then worry about extra spaces if I've got them. Okay, we will continue to put electrons around our atom until we've reached its octet. What is nitrogen's octet? 8 electrons. Have we reached its octet? Yes. We now move on to our next step. Continue adding until we reach our total electrons. What was our total electrons? 8. How many have we added? 8. What does that mean? Next rule. Our next step. What's our next step? Convert our pairs into a line. What I would recommend you do is erase. Okay, everybody hates that rule. You drew it, now you got to erase it, but deal with it. Anywhere we have a pair of electrons in between, we'll go through and erase and turn into a line. Have we satisfied our octets on all the atoms? Yes. How many electrons are around hydrogen?
2.
It's not 8. Why is it not 8? Hydrogen can only handle 2 electrons. How do we get 8 electrons around nitrogen? I don't see any dots around nitrogen. Each of those lines represents 2 electrons. We can count those 2 electrons for all of the atoms connecting it. So we've got 8 electrons around nitrogen, 2 around our hydrogen. Okay? So we can skip 6, don't have to worry about it. Our last thing, assigning our formal charge. Remember, we adjusted that. It's no longer that big fancy rule. We're just looking at assigning it to the molecule. What's the charge on our molecule? How do you know it's +1? What was that? True, but how do you know it lost 1? You had to know the charge to figure out that it lost 1. Thank you. Upper right-hand corner of the problem that we were given. What does it say? Charge is +1. How do we assign that in our structure? We can go through, put brackets, and put the plus in that upper right-hand corner. Okay? We can get lazy on that. You'll notice on your exams you will probably see this symbol. That's not 7 plus. That's a lazy man's bracket with the plus symbol. Works just as well. Okay? Questions about that? You ready to see some resonance? Yeah, there's the enthusiasm I like to hear. Okay, so let's try SO3. How many electrons does sulfur bring in? How do you know it's 6? Sixth column, I like it. What does oxygen bring in? 6, how do you know it's 6? 6 columns, still like it. How many oxygens are there? Do we have any charge? Nope. What's our total count? 24 electrons. What's our next step? Central atom. What's our central atom? Why sulfur? Oxygen is closer to fluorine, which means oxygen is more electronegative. Sulfur, by definition, will then need to be less electronegative. Remember, central atom is chosen based on electronegativity as a first pass. So our central atom will be sulfur. Okay? We can now scatter our oxygen atoms around it. Okay? You can scatter them any which way you want, but I'm going to scatter them this way. Why would I scatter them this way? Okay.
Will we get dark points if we
No.
don't put them in the right
Nope.
configuration?
Nope.
Okay.
I scatter them this way only because I know what the answer is. So I know that that's how it's going to end up looking at the end. Okay? For you guys, let's go and adjust that because how many of you know the answer? Let's try that. Okay, 2 of you. So the rest of you, since you don't know the answer, let's stick with our standard format. Okay? Is that different than if we drew it this way? No. They're all equally valid as far as scattering. I like the spacing better here, though. All right? What's our next step? Add our electrons in pairs, starting with what? Rule number 3, add the electrons to most electronegative. Which element was most electronegative, oxygen or sulfur? Oxygen. So we go through an atom in pairs. That was a horrible looking electron there, but that's close enough. Sorry, I should have done that one in 8 first. We've got 8 electrons around each of our oxygens. 8 times 3 is 24. Can I add any more electrons to the structure? Why not? That was the total valence count. All right, what do we do now? Erase. Technology is fun. And turn it into a bond. Are we done now? No, what do we do now? Kind of going towards resonance, but I don't want to hear that quite yet. Check octets. Verify your octets are satisfied. Your oxygens. We've got 1 lone pair, 2 lone pairs, 3, which gives us 6. We can count the bond as another set. So we've got 8 electrons around the oxygen. What about our sulfur? There's only 6 electrons. You mentioned a lone pair. Where's the lone pair on the sulfur? So let's go ahead and draw that lone pair so we can see it, right? Is that correct? What's our electron count now? 26. Can we add that lone pair there? No. Okay. So sulfur has only 6 electrons around it. How many does it need to have? 8. This means our structure is not complete. We now need to move electrons to satisfy it. Okay? So where do we have electrons nearby to satisfy it? On an oxygen. So let's take the electrons on that rightmost oxygen, let's give them to sulfur. Cool. Sulfur now has its octet. Oxygen just lost it. Okay, so when we move the electrons, we cannot pick them up and both shift them over. What do we have to do? We're going to share them in between. Well, if we share electrons between those atoms, what did we just make? Another bond. We now have two bonds or a double bond. Okay? Why did we take those two electrons? Closest is an interesting theory. Why didn't I take the one from the left? What would happen if I had done that? Let's make those orange electrons now. What would my structure look like? Jeez, it's a lot of freaking dots.
You forgot the two dots on the right.
Oh, no, it's the orange color. They are there on my screen. Are those the two dots you're talking about? Yeah. Did I have to pull it from that one? What if I pulled it from the top one? So this brings up the fun question of resonance. On the exam, what's your answer? Which answer is correct? All three are correct, which means what do you need to supply on the test?
All three?
All three. All three must be specified. Otherwise, you have not accounted for the correct answer. If you supply only one, that is a really good first step. I'll give you kudos for that. You'll get some points. You'll probably get half the points. Okay? But you will miss some points because you are claiming that for the structure of SO3, there's only one structure for it. It's not true. There's three. Okay? So you have to specify when you get resonance all three structures. Okay? Or however many resonance structures there may be. Okay? It can get up to upwards of 10 possible structures. It can be as few as just one extra structure. It just depends on the situation that you're working with. Okay? Do we have our final answer? The last thing that we would have to look at would be charge on our molecule. Are any of our molecules charged? No? How do you know that? Upper right-hand corner of our formula shows what charge? No charge. Okay. One extra little bit of information so that we can help see that these are resonance. You will commonly see this double-headed arrow between it. What that arrow is saying is that the electrons to make that extra bond, that double bond, are potentially coming from all of those oxygens. So we're saying all of these are now related as one big group. Okay? Makes a huge difference in the overall chemistry of the molecule. You need to account for all of them. Questions about it? Okay. Everybody loves resonance. And by loves, I mean you need lots of practice with it. So I will tell you right now, we will start Tuesday with carbonate. What's the structure for carbonate? CO3 minus 2. So it's going to do two big things for us. Number one, we're going to see resonance. Number two, we're going to see what we do with the minus 2. Okay? Feel free to work on that over the weekend to get used to that. That does not mean we're done yet. Sorry. Just giving you a heads up. Okay? Questions about Lewis structures? Okay. We're going to go through a couple quick definitions on some new types of bonds. We've got something known as the coordinate covalent bond. If we take a look at O2, so a molecule of O2, and react it with another atom of oxygen, we can make something known as ozone, O3. When we go through and draw that, okay, what they're trying to represent is that if we look at the electron configuration for our O2, or our Lewis structure for O2, everything looks nice and happy there. Okay, we don't have any issues. Everything's got their octets. I don't know what to draw on that, so I'll just not draw anything. If we take a look at the oxygen atom, what's the issue with our oxygen atom? It's missing a pair of electrons, right? So what could we put into a 2-electron hole? 2 electrons. Where do we get those 2 electrons from? The molecule of O2. Okay? So the electrons that we end up doing to make that bond between them, right here, came from only one of the oxygens. Our rightmost oxygen supplied a hole, the leftmost supplied an electron, or the pair of electrons. If we're forming a bond in that fashion, it's known as a coordinate covalent bond. It's still a covalent bond, but we aren't bringing in equal sharing of electrons. One supplied all of the electrons. Typically, where you'll see these coordinate bonds is with transition metals. Okay? I would never have picked ozone as an example, but hey, it actually works. Okay? Why would we see it for transition metals? What charge do you see on transition metals? What charge do you see on all metals? Positive charge. Can a positive charge supply electrons? Nope, because it's positively charged. So our metals can do coordinate bonding with nonmetals. The nonmetal can come in and supply the electrons to help out that metal. Okay, so that's the more common place you'll see it. The next one is actually a misnomer. Okay, we can refer to the concept of hydrogen, and I'm going to call it, or attempt to call it, hydrogen not bonding. Why do we call it not bonding? Is it a bond? No. A bond implies sharing of electrons between atoms. A hydrogen not bond is not sharing electrons. There is no sharing of electrons in that case. It is a weak interaction. Okay? You could also refer to it as a pseudo-electrostatic interaction. How do you get a hydrogen not bond? What's the first thing you think you need to have? Come on now. It's in the name. You need a hydrogen. Okay? What we're trying to look at is a very strong interaction. Okay? So that hydrogen needs to interact with something else really, really strongly. When are we going to see strong interactions between particles? When we have negatives and positives. Okay? If we have a positive atom, it's going to want to interact really, really strongly with a negative atom. What charge would we expect to build on a hydrogen atom? Partial positive, right? Why partial positive? Why is hydrogen typically a plus charge? Why does it lose electrons? Still right. It could still gain electrons and look like noble gas. Everybody's favorite, like, 4-syllable word.
Resonance?
Holy crap, no, that's like 6 or 7 syllables. Electronegativity. Hydrogen has very low electronegativity. Did you count out the syllables? What was it? 8 syllables? Yeah. Okay. Very, very low electronegativity, which means it does not want to hold on to its electrons. So something more electronegative than it can take electrons from it. What would we expect our hydrogen to then interact with if we were going to generate a strong interaction? Whoops. What should that something have? Negative characteristics, or a partial negative. Okay, now comes the kind of trick with our hydrogen bond rule. We need this partial positive and partial negative. How can we make hydrogen partially positive? What does it need to be attached to? The negative part I kind of agree with. I don't like the partial negative in front of it. It will be partially negative. Why would it be partially negative? What element would take things away from hydrogen, would take particular electrons away from hydrogen? What type of element? Not to be like pointing anywhere to a particular side of the periodic table. A really, really Electronegative element. The more electronegative the element is, the more likely it's going to take electrons away from the hydrogen. Okay? So on both ends of this hydrogen bond, we need a very electronegative element. The electronegative elements that will satisfy the requirements to make that hydrogen positive enough to make a hydrogen bond happen to be kind of funny. Funny. Yeah, kind of. It has to be fluorine, oxygen, or nitrogen bound to that hydrogen. If we do not have a fluorine, oxygen, or nitrogen bound to our hydrogen, we do not get hydrogen bonding. What does our partial negative need to be? Equally funny. Okay, I thought it was more funny that time. Also has to be fluorine, oxygen, or nitrogen. So when we look at our classic hydrogen bonding compound, water is it. What does the red dot mean in our structures or drawings? That red dot is an oxygen. What are the white dots, which I'm going to make blue? Hydrogen. What happens? We're looking at aligning the partial positive charge on one hydrogen with the partial negative charge on that oxygen. The interaction between those is known as hydrogen bonding. Okay, so let's throw in a new one. Let's throw up, that was a bad phrasing. Hopefully no one's sick. What interaction is happening here? As I highlight it in blue. What is this guy? Why is it not a hydrogen bond? What was that? The hydrogen is not partially positive. How do you know it's not partially positive? It's not bound to fluorine, oxygen, or nitrogen. That is not a hydrogen bond. Okay, here's the next kind of trick question. What is that interaction? What do we have in here? Tell me what that interaction is known as, and don't tell me sharing electrons. It is sharing electrons, but I want more detail. Why covalent bond?
Because they're both non-metals.
Okay, I see where you're going with that. Yes, they are covalent bonds. Can you take that a step further? Someone else run with that? Is it polar covalent or covalent? How do we decide the difference? There's two ways you figure it out. Number one, you look up the difference in electronegativity and you calculate it and determine what that difference is. Or, two, you remembered what I told you a nonpolar covalent bond was. Anybody remember that I told you? The same and one extra thing. Hydrogen to carbon is a nonpolar covalent bond. You don't need to know the electronegativities because I told you your rule on what that was. Whether you decided to remember that or not, that's entirely up to you. Okay? If we try to describe that bond, we could say it is a nonpolar covalent bond between hydrogen and carbon. It is not a hydrogen bond. Okay? So hydrogen bonding is very, very specific, arguably one of the most important intermolecular forces that you could deal with in the world. Any idea why? What molecule shows you hydrogen bonding? Water. Why is water important as a solvent? What is 80% of our planet made up with? Water. Okay? Why is that important? Well, all of our life is based around water as well. Okay? We're made up of a large portion of water. When a protein decides to interact with another protein, what's going to be the intermediary thing that's going to get in the way? Water. What causes proteins to fold and take the shape that they do? Water. What causes proteins to unfold? When we take them out of water. Okay? Water is hugely important, and it all comes back to this intermolecular force. You will see these rules show up again and again and again. Okay, questions about any of that? Okay, now what we're going to end with is pretty much where we're going to pick up after we do the Lewis structure for carbonate, is what's going on with shapes. If we looked at the Lewis structure for CH4, and what I'm about to do is exactly why I would say people get problems with Lewis structures, because I told you what? We had 7 steps to go through and draw a Lewis structure. How many of those steps did I actually follow? I would argue none of them, really. Okay, why? Because I've gotten used to those steps and I can internalize that. You don't have that used to yet. Until you're used to those steps, you better draw everything out. Okay? So we've got CH4. What's the issue with this? What's the difference between that top hydrogen, let's call it our purple hydrogen, and our orange hydrogen? Or our blue hydrogen? Or now our red hydrogen? What's the difference between a hydrogen atom and a hydrogen atom? Nothing. What's the difference between a hydrogen-carbon bond and a hydrogen-carbon bond? Nothing. What are those atoms all going to do? The exact same thing. Okay? They are all going to equally repel away from each other. They do not want to be near each other. Why? They all have the same mass, the same charge. We could look at the hydrogen nuclei. They're all positively charged nuclei. They all want to get away from each other as much as possible. We could also look at the bonds. What's in that line? 2 electrons. What's in that line? 2 electrons. What are those electrons going to do? Get away from each other as fast as they can. So when we look at the Lewis model, we want to make sure that our model accurately represents, as best we can, the reality of the structure. So we go through and say, well, it needs to be exactly the same. So what's the bond angle between our purple hydrogen and our orange hydrogen? What does it look like? I know, pretend I drew it straight lines. About 90 degrees. What's this one? This one? That one? So what would we say? That looks pretty good. They're all pretty equal. Are they really all equal? I remember I asked the question. What's the bond angle between those 2 hydrogens? 180. Are all the bond angles exactly the same? No. Lewis's theory does not explain what we would understand of electron repulsions. It gives us a good idea of what bonds are present, but it does not explain the 3-dimensional structure. Our 3-dimensional, oh man, I forgot to bring them in here. Our 3-dimensional structure is going to show those hydrogen atoms getting as far away from each other as humanly possible. To do that, okay, or to visualize that, this is where this one becomes a challenge. How many of you can see well in 3 dimensions? Like in your head, not like looking out. That's different. You close your eyes and you can see in 3 dimensions. What shape do you get? Okay, so since that option failed, let's try another one. Maybe you won't volunteer for this one. Dungeons and Dragons fans? D&D? Role-playing? The die? Oh, okay, that was a loss. Try it. 4-sided object. 4-sided object is known as a tetrahedron. The shape that we generate here is a tetrahedral shape. If we were going to attempt to draw that, it's going to look really awful because I forgot the model kits. We would put our carbon and 2 of those hydrogens in the exact same plane. We can do it kind of with my hand. So my wrist is a hydrogen. The hydrogens are also out at my fingers, and the carbon is the dead center. Oh, as my hand spasms. Right in the middle. Okay, what we have there is a tetrahedral shape. If we were going to try and draw that, we're going to put as many of those atoms in the same plane as possible. In this case, I'm putting the hydrogen with my, index finger, the carbon, and my wrist all in the same plane. I even drew it according to that. Where's my middle finger aimed? Okay, so if we looked at how that's aligned, that's aimed out towards you. How could we draw that? Okay, well, this could be fun. What happens when something gets really, really close to you?
You want to back away.
It looks like it gets bigger. So what are we going to try and do when we draw?
That's a solvent. We use 3-foot space.
3-foot space. Okay, let me try it again. We'll put our hydrogen as a wedge coming out at us. It's coming out of the plane of our paper. What about that other hydrogen, my thumb? Where is it? It's aimed away from you. To represent that, we could make it look smaller. That gets difficult to do. So instead, we draw a dash. What we're trying to now represent is that three-dimensional structure with these extra little lines and wedges and dashes. Okay? As much as everybody loves wedges and dashes now, you don't have to stress too much about it. What you need to know is what the shape comes out to be. Okay? And when we draw it, so when you look on a piece of paper, what do those symbols mean and what do they in general look like? You don't need to know how to draw it. Okay? So that gives us this tetrahedral shape. But what happens if we don't have 4 bonds? Well, that's going to change the shape because we have differing amounts of electrons around it. So Vesper theory goes through and it explains the shapes of molecules based on how the valence shell electrons, in fact, the valence shell electron pairs repel each other, or the Vesper theory. So all we're doing is very hand-wavy argument saying these things don't want to be near each other, they repel away. So as a first pass, what we end up with is something known as the electron geometry. How many groups of electrons are around an individual atom? That's our electron geometry. The other thing we could look at is the molecular geometry, which is what most people are used to seeing. The molecular geometry is in reference to the atoms. Where are the atoms located? Why would we be used to looking at the atoms and not the electrons? Which is bigger? The atoms are much larger than an electron. Okay, think even about our symbols. Looking at a dot versus a giant letter. Okay? So what you're going to be responsible for is, given an individual formula, be able to draw it, and then predict what shape it should have. Okay? So I would expect you to review this material, get an idea on what's happening. The next few slides kind of summarize this. So we can look at the number of electron groups, a representative molecule, and the electron geometry shape that comes out of it. Are we going to encounter another issue? Yeah, I'm sure is a good guess. So there's another drawing for it. If we look at the Lewis structure for NH3, this is what I'll end on. Feel free to pack up. I'll start again with this. Are all of the electron groups the same around that nitrogen?
Yes.
We have 4 groups of electrons, but in one case, we have a bond, okay, where we're sharing electrons, and in the other case, it's a lone pair. The example, since you're close enough to pack up, I'm going to stay on now. Let's share these 2 electrons. If I'm the non-bonding pair, where are those electrons? I'm holding on to them, right? What happens when I share them? Sharing. They now move away from them. Are those electrons in different locations? Yeah, they're going to take up a different volume, which means the shape will change. Okay? So we'll pick up there. Hopefully your lab will clarify some more of that, give you that.